Yeah. Okay, let's start. Yes, question was when the exam is. It will be at some time in March. I don't know it more precisely. Don't end it. So now. Okay, I hope you can see my screen now. And today we are going to make a big step forward because now we are going from, let's say, individual devices to more complex systems. And the main aspect here is in order to predict reliability of systems is so-called methods of risk analysis. So it's not only analysis, but it's also prediction methods. And that's really important because there are many standards, for instance, in the medical area or in the aerospace area. And all of these require that there is a risk analysis of a system. And today we are going to see several such methods, and also are going to enter in such methods. There is mainly three types of such analysis. It's a failure mode analysis. So that means how can it fail? And that is a qualitative analysis. And then we have quantitative analysis. That's failure rate, for instance. And also we have system state methods. That means we do not just look in a way, it is a system, a subsystem, and so on, in a let's say, in terms of a structure, but it is rather in terms of a process. So system is in one state and it goes to another state. And depending on in which state it is, then what can be the next state, for instance. And in that way, we can also predict some developments. Yes, it's not a static structure for which we predict reliability value, but it is rather what are probabilities that has happened or that has happened, and leading to a certain state. Okay. Then we have in the failure mode, we have inductive analysis methods and deductive analysis methods. Deductive methods are rather based on Boolean mathematics. So if that happens and that happens, then next thing will happen. Yes. And inductive balance is more yes, in a logic way of how things develop, also partly based on physical events, not just on Boolean operations. And here the most important method is failure mode and effects analysis, that we will see in more detail. In the failure rate, we have parts count method and parts stress method. Both are very similar. Both are methods adding up just failure rates, you could say. Yeah. So you have a system consisting of 10 components, and the failure rate of the system is the sum of all failure rates of all components. So in the parts count method, you use standardized values, and in the parts stress method, which is physically more correct, you take the failure rates which are more relevant, as these are based on the real stress conditions. So for instance, if you have a printed wiring board, you could say, okay, all devices have that failure rate, and the total printed wiring board has then the sum of all values. But when you take parts stress method, for instance, you can say the power semiconductor is 100 degrees hotter, and the microcontroller 50 degrees hotter, and then you take the failure rates based on these temperatures, for instance. And these failure rates are, of course, higher. And in that way, yes, the relevant method is parts stress method. Also here, for failure rate analysis, we will see two things, how to represent it. One is to represent failure, and the other is to represent the probability of function. It is, in the end, it's the same, because function and non-function are complementary properties. And in that way, we will see that later on, maybe in 2 sessions or so, we will see system state methods, which is mainly Markov chains and Markov processes. Okay, so that's the overview. And let me say, risk analysis is I would say, it's the heart of that lecture also. Yeah, it's really important to know at least quantitative and qualitative methods. And if you design implants, for instance, you will be requested to give such information and data on such analysis. Okay, there is a simple model, and that model is the so-called reliability block diagram. Imagine you have 3 resistors or more resistors in a series, yeah, or you could also say conductors, yeah, all carrying the current, and the current is the equivalent for the function of that system. So that means if you break one of these conducting elements, the complete current will break down, and you will have no more function. And it is not in a way that it's like Ohm's law or so, but it just means if in that chain one is eliminated or carrying no more current or function, then the complete function will be eliminated. So that's a series structure, and that is a so-called reliability block diagram, RBD. The reliability block diagram is the diagram that is the diagram that models the function. Yeah. And now, over time, as we know, the reliability will go down for every element. And now you want to know the question, you have two elements and both elements must function after a certain time. Then you could say the reliability of one element, E, is RE, or R1 or RE is RE of t. And of the second, it is Rj of t. So reliability has gone down, and reliability, as we know, is just the probability of the probability of function. Yeah, so we have now here time, and we have here two reliabilities. So that is E, and that would be J. Okay, the probability that E works and J works is R E multiplied with Rj. So let's say if you would have a high probability that both will work, you could say, for instance, with 90% probability, in a simple way, you could say I have 10% here, that one will not work, 10% here, so it's roughly 80% that both will work. But if you multiply it, you will see it's 0.9 times 0.9, so it's 0.81, 81% of probability that both will work. And that simple model can be generalized to n elements. So if you have n elements, the system reliability will be just the product of all reliabilities over T from element 1 to element n. Okay, when you have that, you can say what is the Fehler function of element E? That is 1 minus RE of t, and that is, if you assume an exponential distribution, it is 1 minus e to the power of minus lambda t. In very short times, short always means significantly shorter than the mean time to failure of that element. Then you could say the failure function or the failure probability is roughly the failure rate multiplied with the time. So here, lambda to the power of -1 is just mean time to failure in an exponential function. Okay, so then when we have that here, we can describe the individual RE by that exponential function. And so here we see that RE of t is e to the power of minus lambda e t. And then we multiply that. Still quite simple. And Rs is e to the power of minus lambda e t. Yeah, if you multiply that, you can also say you take that in the exponent and add it in the exponent. That's simple mathematics. And then you can replace the sum of lambda E just by lambda S as the lambda of the system. And in that way, you will see the failure rate of the total system is the sum of all individual failure rates. Okay, in that way, we have seen in a serial system, we want to know the failure rate, we add them all, and then we have them for the system. If all conditions for all elements which we add up are the same, as I said previously, it's a parts count method. Yeah, you just take some datasheet values and add them up, and then you get a certain value. And if you take it for the individual stress factors, then it's the parts stress method. The TS, or also called mean time to failure, is just the inverse of the lambda of the system. That means failure rate is the inverse of the mean time to failure, or mean time to failure is the inverse to failure rate. We already know that the assumption of an exponential function is, yes, how to say, it's a crude simplification. And a better method for description of failure rate over time is, of course, the Weibull function. And that means Weibull function leads either to a decrease of failure rate if that beta value is smaller than 1, or it leads to increasing failure rate if that beta is larger than 1. And if it's just 1, the beta, then we have the exponential function. Okay, so exponential function is a special case of Weibull function. Now, again, we can say here that Weibull function, which gives us the failure probability, or maybe better, the failure function, leads to the reliability function, and that here is e to the power of minus t divided by tau to the power of beta. Beta is that in German called Weibull modulus, and that tau is the characteristic lifetime. And if every element E would have a different beta E, then we would end up with that formula, e to the power of sum of t to the power of beta E multiplied with 1 divided by tau E to the power of beta E. Okay, we will not be able to solve that further on analytically. So in many cases, we can assume that beta is equal for all elements. That's especially the case when all elements have the same failure mode. Then frequently the beta is same, or often beta is assumed to be a certain value, like 4, for instance. And in that case, we can again analyze the characteristic lifetime, and in that way, the characteristic lifetime of the system is taken by summing the inverses of the characteristic lifetimes of all elements here. And of course, it's the inverse of the characteristic lifetime. Okay. On the other hand, in some cases, we want to be safer against misfunction. And in that way, we can think of another structure of our elements is where the elements are in parallel. That means redundancy, because we have that functional current here, and it can go through 1, 2, 3. In that case, we do not assume the function is increased because we have 3 elements, but it's just all 3 carry the function. And also, first of all, it's not considered, let's say, what the performance is if there is only 1 or if there's 2 or 3 elements. It's just functioning. And so imagine number 1 would be failing. Then still we have 2 elements. If another one would fail, then we have 3 elements. And if the system is functioning when we had 3 elements and only 1 is necessary, then it is 1 out of 3 redundancy. In case, for instance, we would only allow 1 fails and 2 have to work. It is still functional. Then we have 2 out of 3 redundancy. When would it be sensible? We still need, let's say, we still need 2 elements for the system to function. In which technical case could that be necessary? Yeah. Yeah, that is correct. If you only have 1, you don't know, is it correct or not? Sensors, it's the most important thing. But also here, you can say performance still matters. For instance, there always have been aircraft, for instance, that had 3 engines, yeah? And it was possible with these aircraft to fly them with 2 engines, but not with only 1, yeah? So power would not have been sufficient, or aircraft can be asymmetric, yeah? And then you cannot really fly it. And in that way, there are reasons, but the most important in electronics, the most important reason is you want to compare. Okay, so that's redundancy. And here we can say let's go to 1 out of 3 redundancy. And then we can ask ourselves, when will that system function? And you can say only when 1 is functioning. but you can also make the complementary question, which is more sensible here. When will that system fail? And when will it fail? It fails when 1 fails and 2 fails and 3 fails. And how do we describe the probability of failure? By which function? Failure function. Okay, so failure function gives us the complementary. Yeah, you could say it somehow goes up here. Yeah, that's f of t, and in that way, you can take an approach where you say, if all fail, then it's a probability that 1 fails, 2 fails, 3 fails, until n fail. And so it's a product of all probabilities of the failure functions. And again, you can multiply that, and then you end up with 1 minus e to the power of minus lambda t in the case of exponential function. And you can also say the reliability function is, of course, again, the complementary, so it's 1 minus that complete product. So in that way, we can calculate the system's failure function and reliability function. Getting a failure rate then is not so easy. So we can, here we take it only for 2 cases. You can always calculate a failure rate numerically based on the formula. The failure rate h of t is f of t divided by r of t, and that is df divided by dt So in that way, we can get the failure rate. Yeah. First derivative of the failure function is the so-called density function, and dividing that by the actual reliability, that is the failure rate. Okay, we already know that from the beginning of the lecture. But taking that for a complex system is not so easy in a analytical way. So here we take it just on the basis of 2 elements having the same failure rate. And yes, so the system reliability again is if we take that product, it's the reliability of the element 1 plus reliability of element 2 minus reliability of element 1 multiplied with element 2. That is just because Fs is F1 times F2, and then you multiply that, and in that way you just get that reliability of the system. So if you replace these factors here just with the e to the power of minus lambda, then you, because both are equal, lambda 1 is lambda 2 is lambda. You get Rs of t is twice e to the power of minus lambda t minus e to the power of minus 2 lambda t. You can try to resolve that for that formula for lambda. So that's, you will not succeed. So you have to go to the way the mean time to failure is the integral from 0 to infinity of Rs of t. And when you integrate that, you end up with MTTF, which is 1 divided by lambda of the system again, is 2 divided by lambda minus 1 divided by 2 lambda. So that's the special case of two redundant elements having the same failure rate. When I'm holding the exam, I often find out that such formulas are learned by heart by some. Yeah, for me, I think it's always easier to keep in mind how that is derived. Yes, and the most important thing is for redundant system, you multiply the failure functions, and for serial systems you multiply the reliability functions. Okay, and when you have that, when you have one of these functions, failure function or reliability function, you will always be able to find out all of the other functional dependencies like mean time to failure, failure rate. Here I was writing h of t because here we not yet know if it's constant or not. And if we know it's constant, we call it lambda. If it's not constant, it is h of t. And that is density function divided by reliability function. So in that way, we are able to derive all of these properties. Generally, so that was a little mathematics, but now we're looking more at engineering questions. And there are three types of redundancy, which is called hot redundancy, warm redundancy, or cold redundancy. Hot redundancy means, like in the aircraft with the 3 engines or 4 engines, all engines are running, and that has several advantages. What are the advantages? All are running. Imagine you could have another situation. You have 3 engines, and you only have 2 running. And if one is making problems, you turn it off completely and turn on the spare motor. What would be the advantage of having all 3 running? Yes, though that means the lag time is very small, or by definition it's 0. And it is there, it is in operation. And what's the disadvantage of having all 3 running and not having one in spare? Yeah. Yeah, that is one possibility. We will come to that later on. Another thing is, if some element is running, its failure rate will be higher than when it's not running. Yeah, because operation means stress, voltage, electrical field, current density, temperature, power, and so on. So that means hot has also disadvantages because we have full load on each element, and the reserve element and the primary element, when they are together active, and they have the same failure rate. That is important. So both have the same lambda and no lag time. Then we can have warm redundancy. So the redundant element is in a standby mode. That could be, for instance, in some computer systems. You have a second backup, a second computer, and in former times, big computer systems, it took them quite some time to boot up. Yes. And so if you have it already, let's say, entered the boot routine or such a thing, so only the final step to really get it into operation will not take much time, and also the load is lower than the load of when it's fully operated, and that could be such a thing, and that is called warm redundancy. Or if you have the engine, you could say, yes, I have two engines running fully, and the third engine, it's just it's running, but it's in idle mode, for instance. And so in that way, it takes a certain time until the spare element is in function, and it has a failure rate, but the failure rate is lower than the normal hot failure rate. Yeah. And then we have cold redundancy. That is a spare element that is not in operation at all. What is a good example of such a spare element we have? In a car, for instance? Yes, of course, spare tire. I would say that's a classical redundant element. You could also think of having four wheels in a car. Yes, you also have trikes. Yes, some kind of cars having only three wheels. So you could say at least the fourth wheel in a car is some kind of hot redundancy, but the spare tire is something like cold redundancy. And of course, it takes time to take it from the trunk and to install it. Also, spare tires often are as new even after 10 years of being in the trunk. Yes, so you see their failure rate is more or less zero. Yeah. Okay. In that way, we have these three types of redundancy, and that means one thing for the reliability block diagram. The most important part is how we treat the failure rate. Hot is the same failure rate like active element, because both are active. Warm means a smaller failure rate, and cold redundancy, by definition, the spare element has zero failure rate. Okay, here is that I took from the book of Birolini, Reliability Engineering. He has the different cases, and as I said, sometimes I'm astonished some students learn all of these formulas by heart. I don't think that makes much sense, but important here is 1 out of 2 redundancy. That's easy. then we have k out of n redundancy. So as I said, it means k must work when we have n redundant elements. And that can be computed by the sum of all n over e multiplied with r e. So yes, for that index e here, that's not an exponent for the RE, and 1 minus R, but that is an exponent here, I would say. One, is it really? No, 1 minus R to the power of n minus e. So here we have it again. That n over k is the binomial coefficient, that's n faculty divided by k faculty multiplied with n minus k faculty. So for instance, here we have if the Fehler function is 10 to the power of minus 3, so 99.9% will still work. So we have 3, the binomial coefficient of 3 over 2 multiplied with 0.999 to the power of 2, and multiplied with the complementary of that 0.001 to the power of 1. So it's really a power and not an index, plus 3 over 3. Then we have it 0.99 to the power of 3. Here the difference is 0. And in that way, we get a value of 0.999997, which is really a high probability of failure, or that means 3 ppm of failure probability. So that is 2 out of 3 redundancy. That is okay. There are other cases. If we have a series and parallel structure, we can build something like a schematic, which has, for instance, in one branch, 3 elements, in the other branch, 2 elements. That is redundancy where both elements are different, the primary and the secondary element. The advantage is that both branches can have different failure modes. Yeah. So if one failure mode occurs, which could be a so-called common mode failure as a result of a common cause, then if both branches are equal, both can fail. And so we can have it here, it's so-called diverse redundancy. And in that way, here we have 3 elements, here we have 2 elements, and then we also have a serial structure. Again, going in a systematic way, we can proceed as follows. Everything that is in a string can be computed. Always, if there's a string, then we only have 3 elements. For these 2 in parallel, again, we can compute the reliability of failure function, and then we get reliability of failure function of that system, of that part here, and both are in a series. So the way is we compute that, then we summarize that, and in the end, we put it all together, and in that way, we can compute it for the complete system. Of course, if you want, you can also just learn by heart that formula, but I don't think it will help you for your further life. Okay, then we have something. We have some 2 out of 3 redundancy, where we said we must compare something, for instance. And when we compare, for instance, when we have sensors, we need a third element, which is a so-called voter, or some element that decides what to take as true from this. So, for instance, if you have 3 sensor values and 2 are very similar and the third is quite different, you could say, okay, I drop that is quite different, for instance, and depending on what you further want to do in that system, you could either just make an alarm. You say, okay, something is different, something is not okay here. For instance, when you have an anti-brake locking system, and if that system finds out something is not okay, you will have a yellow lamp in your car, and behind that lamp is some writing, anti-brake locking system out of function or such a thing. Yeah. So that alarm means system is maybe shut down or some red lamp goes on. Okay. So then we have so-called bridge structure. I often take that bridge structure without an element in the middle. The question is, when we have a serial system, okay, and okay, that would be our serial system. Of course, that 1 and 2 we could assume to be 1 element, yeah, and 3 and 4 should be 1 element, but the failure rates of 1 and 2 just add up, and the failure rate of 3 and 4 also add up. Yes, so we have redundancy, but the failure rates add up. So if we have that functional current, and for instance, if the element 2 will fail, that complete branch will fail. But what would be better? If we would still be able, so here 1 would fail, so the complete branch 1, 2 is eliminated. What would be better is if we have a connection here, and typically we need an element for that connection, but we can simplify it in a way we say, okay, if 1 and 2, if 2 is eliminated, we can have a current going here, or it's going here. So the redundancy between 1 and 3 is maintained. And that's more reliable than when we have just 2 strings in parallel, yes, without cross connection. So that's a bridge structure, but typically here it says E5 is bidirectional. So it says when it comes from E2, it can also direct function to E3, or from E1, it directs it to E4. And that means that's a, let's say, a more clever, function structure. We also can have situations where it's only unidirectional, but I will not go into the details of that. Also here, we have some structures where, for instance, the redundant element has a function for several other primary elements. Yeah. Now, in the unidirectional, that is only so when E3 fails, it will be able to direct E1, E5, E4. But if E4 fails, it will not be able to direct it up here. That's a sense how it works. And here the E2 is some, let's say, some spare element. Some spare element you can use for other primary elements. It's not so easy to have an example, but yeah, maybe you say you have some computer network, yeah, and you have one spare computer which can replace any other spare computer, and in that way the same element or redundant element that is modeled is simultaneously here and here. Yeah. Again, that can be modeled in a special way, but we will not go into the details. So there are many cases, and you will find that in the special textbooks. But what is important, I think it's also easier to keep in mind, is when we have 1 out of 2 redundancy, and we have sensors, and if I would say, when, for instance, when you know that one of the sensors is dead, yes, you could still assume the other one is functioning. Yeah, so you could say, okay, if really that first sensor has a signal above 100% or 0%, and the other is giving an output, then you could assume, okay, that's clear. The first one is still functioning. One is completely dead. But if you have both, let's say, in the range where you could expect a signal, so between 0 and 100% of full scale, and then you must have some comparator which gives a decision, at least that both are different. But in that case, you cannot be sure which one is correct, and then you must turn off the system. Yeah, you must shut it down, or you must have some other solution for that problem, but you cannot rely on the sensors. So that's the reason why we rather have more of these 3, And then we have either majority redundancy, or some, yeah, and leading to a reaction of the system, saying, for instance, two are similar, I take the mean of these, or something like that. So in that way, the probability that we still have an operation is higher. For instance, in an aircraft, when you are flying, yes, what is the most relevant parameter in the flight of an aircraft? So fighter pilots always say you need both altitude and speed. But what is more important? Speed. Too slow, aircraft will not fly anymore. It will drop, stall. Too fast, it will disintegrate. Yeah. And in that way, speed is most important. So if you have several speed sensors, which is typically a pitot tube, if both are giving different signals, you will not just be able to say, okay, I shut off my aircraft in full flight. So you have to have something keeping the system up, and in that way you can have these 2 out of 3 redundancy with some majority voting element, and in that way you can still have information on the speed of the aircraft. Yeah. Of course, you can also have diverse redundancy. For instance, what would it mean in an aircraft if you have a different type of measuring speed? What could you do? What's the most, if you are as a private person, what's the most precise method to measure your speed, or when you are cycling or driving by car? Take a GPS, yeah, and it gives speed very precise, and as long as you are going straight, at least. But why isn't it so feasible to use GPS in an aircraft for speed? No, that's not the most important part. GPS gives you ground speed. And which speed is relevant in aircraft? Airspeed. And in some, how do you call it, jet stream, you can have up to 200 kilometers per hour. This or this, then that means you have to add it or subtract it from your airspeed. Yeah. So a range of 400 kilometers per hour. And that can have an influence of whether you fly or not. Yeah. And in that way, at least then you would need additional information to your ground speed. Am I going west or east or so? And then your speed would be different. But airspeed is not a real speed. Yes, it's relative to the air in which you are. And aerodynamics depend on airspeed, not on ground speed. Yeah. Okay, in that way, diverse redundancy could be helpful, but there are some disadvantages. Okay, but when we have majority redundancy combined with diverse redundancy, which means you have another principle, it is quite quite safe against having wrong values. So that means you have different transducer or sensor principles. You also in diverse redundancy have different assembly and packaging technologies. In real diverse redundancy, for instance, because every sensor or so is having a microcontroller in it or microcomputer, you have several types of microcomputer. You have different different programs, so not the same software. Maybe you have some source code, you can compile it for that microcontroller or that, both in C. It must not be the same C, it must be a completely different one, because otherwise you could have systematic failures. So a good example was, I think it was 25 years ago, one of the first Pentium computers had a bug. The Pentiums then had a arithmetic processor as part of the processor, and that had a bug. And some, I think, multiplications just gave wrong results. Okay, if you have such a thing in a really relevant system, and you make redundancy, both computers will compute the same nonsense, and that has to be avoided. And so for having real diverse redundancy, all of that is different in a very strict way. Okay, but again, why do we have diverse redundancy? There are so-called common mode events, and these can lead to a common, no, there are, yes, common mode events, and these are a result of common causes. And these common causes are the same is happening to all elements of the system. And what are typical common causes of failure? For instance, you have a stroke of lightning somewhere in your power grid, and that gives a voltage peak. And if that voltage peak is too high, it can kill your electronic system. Yeah, in former times, we often had, let's say, maybe 30, 40 years ago or so, when you had a stroke of lightning in a local power grid, all of the TV sets of the people were destroyed. Yes, suddenly you had many households having no more TV set because that was a common cause, and because it also was electrostatic discharge damage, it was also a common mode failure. Yeah. Okay, so having different hardware principles can avoid that. I think the most important common mode failure in history was not so long ago. It was somewhere a little more than 10 years ago. It was Fukushima. What was it? What is it? Fukushima. Yes, and it was not only one nuclear plant, but several reactors close to the sea. And these power plants, they have, yes, you have the reactor with the radioactive material, which gives away lots of heat. So if you turn off that, you still have to cool it, because otherwise all of that would melt down. And so you have very strong diesels, and these engines, they can pump the water to the nuclear vessels in order to cool it. And now there was a problem that the basic cause was a tsunami wave, and that tsunami wave flushed all of the diesels, yeah. And so there was no more emergency cooling for the reactors, and that was the case. The reactors were melting down. Bad situation. At that time, when Fukushima happened, we just had several professors from Japan as guests. I was still wondering here in the TV, and so there was much how to say turmoil. These Japanese, I don't know, they didn't look very impressed, so I don't know whether they noticed what really had happened. Yes, but in the end, that was the reason why we have diverse redundancy. I think they had 5 or so or 6 diesel engines. Yes, you have redundancy, and I heard about a similar thing in a nuclear power station, I think in Finland, where they had a problem with lightning, yeah, also eliminating redundancy. So there was no accident, but it already was dangerous. Okay, now let's go to another representation of such serial and parallel systems. We can also model it with so-called fault tree analysis. And fault tree means the following. We have some base events. Base event 1, base event 2, base event 3. And the combination of these events leads to other events or not as a consequence. And one of the possibilities is AND structure. So we have one base event 1 that, let's say, 1 fails, 2 fails, and 3 fails. Then the system will fail, for instance. What kind of redundancy is it? 1 out of 3 redundancy. So all have to fail, and then it is an AND multiplication. And you could, in that case, you would just multiply the probabilities of failure. So for instance, here that would be 5 times 10 to the power of -4. Second would be 10 to the power of -3, and here it would be 1.5 times 10 to the power of -3, -4, -3, -3 is -10, and 5 times 1.5 is 7.5. So the multiplication of these leads to a failure probability of 7.5 times 10 to the power of -10. That's really a low probability, while 10 to the power of -3 or 1000 ppm is already high probability, at least when you deal with lives of people or such similar values. Okay. In the end, we have the AND operator, but we have also seen behind the reliability block diagram, we also have the AND operator. Okay. Here we can also have the OR operator. That means if base event happens with a probability of 10 to the power of -3 and the base event 2, or the base event 2 with the same probability happens, we end up with roughly a probability of 2 times 10 to the power of -3. We adding up normally is not quite correct, because mostly it's based on multiplications. Yes, if we add up, it's typically when we have small probabilities or very short times, then we get some estimation of that. Otherwise, we would have to go for reliability. Yeah, that would be 0.999, and here also. Yes, multiply it. And in the end, when we take the complementary, we end up with ZFS. Okay, but that's a fault tree. Most important thing is fault tree is modeling the failure. Reliability block diagram is modeling the function. In some cases, it is much easier to take the reliability block diagram. Sometimes it's much easier to take the fault tree. I will not go into the details of the fault tree. In fact, for instance, if you try to model 2 out of 3 redundancy, it is already, you will already have a really complex fault tree. In that case, it is better to have it with a reliability block diagram. In other cases, it is easier to use a fault tree. Okay, there's lots of literature and so on, but I think showing these is the most important for these inductive methods, which can also be used for failure rate computation. Okay, now we would like to see a more general method to compute reliability function and failure function. And we can start that with that element which where we have in fact two different functional elements, and both are redundant, and we have that cross linking. For instance, what could it be? It could be a sensor with the instrumentation electronics, and another redundant sensor with instrumentation. And if either one of the instrumentations fail, then we still have redundancy in sensors, or if one of the sensors fail, we still have function in in the other two. Okay, now we can ask ourselves how many possibilities do we have for the system to be in a certain state? What could be different states of the system? For instance, one state would be 1 is failed, or another state would be 3 is failed, or another state is E2 is failed, and another state is E4 is failed, but the more interesting is if we have combinations of these. Yeah, for instance, we could have 1, 2, 3 is failed. Yeah, that's another state, or all are failed is one state, or none is failed. So how many states do we have? Yes, 2 to the power of 4, it's 16. With the states, the interesting thing is here we only treat binary states, yeah, failed or not failed. But you could also treat ternary states. For instance, functional failed in that way or failed in that way. For instance, when you have a mechanical switcher relay, for instance, you can say it's the state of the reliability state is the relay is functioning. The relay is failed open, or the relay is failed close. That can be important. Or where is it also important is a valve, for instance, in a chemical plant or in a system which is used for giving doses of drugs into patients or so. The valve switching that could be functional. It could be failed open. Then the patient will get all of the liter of drug, yeah, hanging in the bottle, or it's closed, then the patient gets nothing. So that's different, and that would be ternary states. That can also be modeled, but here we only take 2 states for the beginning. Later on, we have more. So we can say the following. We just do it in a systematic way. We say we have the 16 cases, and the first case is when it's functional, we always give it a 1, and if it's non-functional, we give it a 0. And so we could say, of course, we could combine it. Easy way to combine it is we have 1 to 8, 1, 9 to 16, 0. Then we make it blocks of 4, 1, block of 4, 0, and so on. Then we make blocks of 2, 1, 1, 0, 0, and so on. And here it's just alternating between 1 and 0. And in that way, we have all of the combinations. Okay, quite simple. Nothing to think about. We could also write a short code. 1, 2, 3, 4 are the elements. And if we make an underscore for that, it means it's down. Okay, that just symbolizes it. But then we have a question. Is the system functional? From that table, it's not easy to see. What you need for that table is you have the structure, either the reliability block diagram or a fault tree. Here we do that on the basis of the reliability block diagram. So it's clear, of course, that all cases where 4 elements, and that's only one case, are down, the system is not functional. We also see that all cases where we have 3 underscores, the system is also not functional, because we cannot have that current through the system. And there are some situations where the system is functional when 2 elements are failed, and some situations where the system is non-functional when. Okay, so in the end, a decision has to be made, and we have to look at the reliability block diagram in order to find out whether the system is functional or not. Up to here, the codes and the table is identical, whether we have that cross interconnection or not. Just by having that cross interconnection, we have more cases here where the system is functional. That's the reason why the reliability is increased. And now, for each of the cases, we can compute the probability that that happens. If we say, for instance, all are functional, what's the probability of that? Then we just multiply the reliability functions. If we have 1 is failed and 3 is functional, the total probability of being in that state is R1, R2, R3 multiplied with F4. You could also write R1, R2, R3, 1 minus F4. Yeah. And 1 minus R4, yeah, it would be the same. So in that way, we have all of the probabilities of the states, and what's the sum of these? %, yeah, yeah. With 100% probability, the system is in any of these states. Yeah, you could say, okay, so that's important. Again, the total is 1. That's also when you do a calculation as a control. If you sum such probabilities and where you know the total must be 100%, if it's not 100%, you know your computation, for instance, in Excel, has some systematic flaw. And in that way, we can compute these individual probabilities. What's the reliability of that here in such a case? How do we get the reliability now? Yes, the sum of all probabilities of functional states. Yes. Okay. In that way, and the failure probability or failure function is the sum of all probabilities where the system is not in a functional state. So in that way, and again, when we have that, yeah, we must. The F is 1 minus R again. But again, it shows us it is much more versatile to do these calculations on the basis of the R and the F function and not on the basis of failure rates. Yeah. Okay. And in that way, we had a first step. And of course, when we have complex systems and we represent them, we have to make the table for that. Maybe that's still easy. The second is decide whether the system is functional, but that can also be in a more complex system based on some computer work. You can make, for instance, some search function which looks if there's a path for that special case, and if there's a path, the system is up. If there's no path, the system is down. Yeah. Okay. In that way, we can have a look at more complex systems. Okay, so for today we are finished. Thanks for your attention.
Professor, hello. Can you hear me?
Okay, see you.
Hello.
Jetzt noch nicht.